Okay, numbers 6 to 13 on page 593. Number 6 says, a photon with an energy of 14 electron volts enters a hydrogen atom in the ground state and ionizes it. Okay, so when it's in the ground state, n equals 1, this energy, it's going to have energy of 13.6 electron volts, negative actually. N equals 2, n equals 3, etc., n equals 4, all the way up to really n equals infinity. And when you get to n equals infinity, this number, negative 13.6, they get closer and closer to 0, and at n equals infinity, 0 electron volts, that's when the electron gets ionized. So how much energy do you need to do that? Well, you could think about EP is equal to EF minus EI. So EP final will be 0 electron volts minus a negative 13.6 if you're starting at ground state, which this question is, which means you need 13.6 electron volts to ionize this. But if we think back to the last half of the unit, remember we talked about a photon coming in the photoelectric effect and an electron being given off. And we talked about the minimum energy that the metal needed before it released an electron. That minimum energy was called the work function. Well, we now know that the work function is the same thing as the ionization energy. So the energy needed to remove an electron from a metal, known as the work function when we were doing Planck's constant, is really also called the ionization energy, the energy needed to make a metal an ion. So if we think back to our photoelectric effect equation, EK max is equal to HF minus WO. In this question, it's actually asking you, what's EK max? What is the kinetic energy that the electron will be ejected from the atom with? So it tells us there's 14 electron volts coming in, and we know that the ionization energy, or the work function for hydrogen, is 13.6. So the energy that the electrons are going to have is 0.4 electron volts. Okay, so just to link the two of them, ionization energy from chemistry is exactly the same as the work function that we've been using in this unit. Number 7, calculate the radius of the orbital associated with the energy level E5 and E6 of the hydrogen atom. Okay, so you're looking for R5, and remember the equation is h squared over 4 pi squared k mq squared times n squared. So for 5, it's 6.626 times 10 to the negative 34 joule seconds squared divided by 4 pi squared, and k we use the 8.988 times 10 to the 9th Newton meters squared per coulomb squared. M is the mass of an electron, 9.109 times 10 to the negative 31 kilograms. And Q is the charge of an electron, 1.602 times 10 to the negative 19 coulombs squared. And then for E equals 5, it'll be times 5 squared. Okay, and so you should get an R5 to be, assuming we don't round too much, 1.323 I'm going to say, I rounded a bit, times 10 to the negative 9 meters. It's really 196507, I think, or something like that. And then R6 will be exactly the same thing. It'll be the H, the 4 pi squared, the K, the M, the Q squared, and this time it'll be times 6 squared. And I'd be pretty tempted, if I got that right answer, to then divide it by 25 and multiply it by 36. and you should get 1.90540297 maybe times 10 to the negative 9 meters. Okay, so this is your R6. All right, number 8. Number 8 wants to know energies associated with the hydrogen 2, 3, 4, 5, and 6. So we're going to use En is equal to negative 13.6 electron volts over n squared. Okay, so which one did they ask? 2 to 6? Yeah. So E equals 2 is negative 13.6 electron volts over 2 squared. So E2 should be negative 3.4 electron volts. E3 is going to be negative 13.6 electron volts over 3 squared. So E3 should be negative 1.51, and the 1's repeating, electron volts. E4, negative 13.6 electron volts over 4 squared, 16. And it should be negative 0.85 electron volts. Wasn't looking at the sheet when I wrote that. I made a mess. Sorry about that. E5, negative 13.6 electron volts over 5 squared. E5 should be negative 0.544 electron volts. And the last one, E6, negative 13.6 electron volts over 6 squared. It is going to be negative 0.377 electron volts, okay? And we're going to use these in the next questions. That's why I wanted to list them all here. Because in question number 9, 10, and 11, they do a whole painful thing, so I'm going to kind of go in order. So 9 says, using the values calculated in number 8, calculate the following energy differences for a hydrogen atom. So the first one is 6 to 5. So it wants E6 minus E5. So E6 was negative 0.37, and the 7's are repeating here. Electron volts minus, and 5 was negative 0.544 electron volts. So you should get an E6 minus E5 to equal negative 0.1662 electron volts. Okay, so now if I wanted to cheat just a little, I'd go down and do 10A, because 10A says use the values from number 9 to determine the frequency of the photons emitted when an electron in a hydrogen atom makes the energy level change. So this is my EP, really, right? And I know EP is equal to HF. Whoops, that's not an H. HF. So F is going to be equal to EP over H. So this, now the negative just means it's emitted, so I'm actually going to drop it. 1.662 repeating electron volts, which of course I have to multiply by 1.602 times 10 to the negative 19 joules per electron volt, and then divide by 6.626 times 10 to the negative 34 joule seconds. And when I do that, I should get a frequency for the first one to be 4.0188 times 10 to the 13th hertz. And while I have that in my calculator, if I was smart, I would then do 11A, which wants the wavelength. So C equals F lambda, so lambda equals C divided by F. 2.9979 times 10 to the 8th meters per second divided by that 4.0188 times 10 to the 13 hertz that we just found, and we should get a lambda of 7.45